5G enriching the telecommunication ecosystem. Abstract: we are at the threshold of 5th generation, 5G, wireless networking technologies to be established and then incorporated into standards. New level scalability needs to develop to construct a design framework for designing innovative 5G-enabled technology solutions. The mobile network of the next generation needs to meet diverse demands. End-to-end, E2E, network slicing is a foundation for supporting diversified 5G networks and is vital to the advancement of 5G network architecture. Providing companies and individuals with real-time, on-demand, all-online, social interface requires an organized E2E infrastructure featuring adaptive, automated, and smart operation during each process. Through 5G, we are driving towards consumer value creation, the total cost of ownership and future networks. A step forward for augmenting existing operations and creating new sources of value. In this paper we are dealing with the potential enablers for meeting required vital quality indicators. Keywords: 5G, cloud native, virtualization, network function virtualization, NFV, new radio, NR. Introduction. 5G is not only about introducing a series of gradual changes over 4G, primarily with regards to the increasing data rate that it can achieve. The move to 5G now also opens up total new application domains, specifically within IoT and the tactile internet, in sharp contrast to previous change measures when moving from 2G to 3G to 4G. The expansion of the reach of operation for mobile networks enriches the environment of the telecom network. A variety of conventional sectors are involved in the construction of this environment, such as the automobile, healthcare, electricity, and municipal structures. 5G is the beginning of digitalization from personal entertainment to interconnection within society. Digitalization provides immense potential for the wireless communication industry, which poses stringent barriers to wireless technologies. 1. New level scalability needs to be developed to construct a design framework for designing new 5G-enabled technology solutions. 5G is planned for 3 different classes of use case: ultra-reliable low-latency communication, URLC, enhanced mobile broadband, eMBB, massive machine-type communication, MMTC. 2. eMBB 5G is intended to span a wide variety of services, however, eMBB and fixed wireless communication networks are expected to have the first practical use of the platform. In many ways, eMBB is an extension of services that 4G LTE networks first enabled. Through offering higher data rates and greater coverage, eMBB provides a more reliable and more streamlined user experience too. In crowded conditions, eMBB is aimed at promoting both higher capacity and increased mobility coverage for commuters. Table I. Use cases for eMBB. eMBB. Lighting fast browsing. Better video calls. Stream UHD and 360 videos. Instant cloud access. To meet this demand, eMBB introduces 2 significant improvements. 1. Shifting to cm wave and mm wave band of spectrum to achieve much higher bandwidth allocation and reachability. 2. To enable massive MIMO and beamforming, designing advanced antenna array that has hundreds of TX/RX antenna elements. The initial deployment of 5G non-standalone, NSA, focuses on eMBB. This offers higher network capacity and modest latency enhancements for both 5G NR and 4G LTE. A multi-tier ranked network deployment, i.e., small cells underlying macro cells, is intended to expand wireless network coverage. 3. At the same time, in the wired core network, the availability of system routers, computationally efficient servers and physical links with high-frequency transmission is surged to handle high traffic volumes and respond timely to demands for assistance. Ultra HD or 360-degree streaming video, and even real-time translation for participants speaking different languages. 4. 3. MMTC 5G address the field of machine-type communication, MTC. It is about machine-to-machine communication. MMTC devices can take advantage of their very low latency and rate requirements to facilitate device simplicity that is supported by an MTC-specific transmission mode network. 5 features of such a transmission method are communications with limited peak rate and restricted bandwidth for the device. Table 2. Features for MMTC. MMTC. Low device complexity, service flexibility. Coverage extension, by 15 dB, long battery life, 5 to 10 years, supports massive number of devices. Since MMTC devices may be integrated with various types of physical artifacts, and in different kinds of environments, they can be located where access from the mobile network infrastructure is difficult to achieve. Taking advantage of the delay-tolerant low-rate specifications, transmission modes with deficient data levels and extremely reliable channel architecture can be implemented, thereby offering a considerably more extensive range of mobile networks. 6. Figure 2, MMTC usage scenarios. The infrequent data transmission per system and the tolerance to delays allow extended battery life. Long battery lifetimes can be given by relaying together with meager data rates, where the substantial path loss is split into two lower loss sections. 7. A scalable transmission is required as the number of MMTC devices can be immensely growing, with probably several 100,000 devices per radio cell. In particular, large system populations need robust multiple access schemes for random access. That can be accomplished by increasing the room for contention, for example, by extending time-frequency domain contention signals, which may be further enhanced by successive interference cancellations. For data transmission, uplink capability for devices with very high path loss can be improved. 8. For such apps, it is useful to assign fine granular resources or overload resource use, e.g. through multiplexing code division. In addition, the purpose of relaying will provide a significant improvement in both uplink and downlink capabilities. An MMTC network is engineered to be latency tolerant, effective for transmitting or receiving small data blocks, and to be sent on channels with low bandwidth. The key performance criteria for a MMTC network service is to achieve a high link density of up to 1 million users per km2, which is approximately 10x times its current highest possible 4G LTE connection. 9. 3. ERLC aids very high reliability with low latency transmissions of finite payloads from a restricted cluster of terminals, being dynamic in compliance with patterns usually defined by external events such as alarms. 10. Low latency allows the optimization of a network to process sublime large amounts of data with minimum delay, or latency. The networks need to respond in real time to a vast volume of data that is evolving. 5G should enable the service to operate. ERLC could be the most exciting addition to potential 5G capabilities, but it will also be the most difficult to secure. ERLC requires a completely different quality of service, QoS, from mobile broadband services. It will provide instantaneous and intelligent systems to networks, while transfer from the core network will be needed. 11. Table 3. Use cases for ERLC. ERLC. Industrial automation. Tactile interaction. Augmented reality, AR, and virtual reality 0020, VR. Urgent healthcare. Intelligent transport. This new wireless ERLC networking will ensure latency is 1 millisecond or less. To achieve low latency at this interface, all devices need to synchronize to the same time base. A further component of the 5G ERLC capabilities is time-sensitive networking. This will allow for time consciousness of the shapers used to control traffic. 12. The architecture of a low-latency and high-reliability infrastructure requires several components: optimized frame structure, extremely quick turnaround, effective network resource sharing and control, grant-free uplink transmission, and sophisticated channel coding systems. Uplink grant-free systems guarantee a reduction in latency transmission of user equipment, UE, by eliminating the middleman phase of obtaining a dedicated scheduling grant. 13. Supporting sporadic ERLC transmissions requires a combination of timing to ensure a certain level of predictability in the available resources, thus fostering high reliability, as well as random access to prevent too many resources from becoming idle due to irregular traffic. 5. A ERLC channeling should be widely distributed at any moment in time, owing to the reduced latency requirements. Complexity, that is essential in achieving high accuracy, can therefore only be attained by means of numerous frequencies or structural methods. A ERLC transmission rate is comparatively small, and the analytical precondition is to maintain an exorbitant degree of authenticity, with a generally little packet error rate, per, then, given the limited block lengths. 9. In addition, the resources assigned to ERLC end user will possibly be unutilized since the ERLC traffic is discontinuous. This is because in the absence of a ERLC transmission the channels booked for ERLC are indolent. Reliability of ERLC will potentially be enhanced by eliminating prevalent assets from eMBB and assigning them to ERLC. 7. Network slicing. Network slicing is one of those principles that facilitates and accelerates digital transformation and achieves maximum growth in the management of resources and financial values in the communications service providers, CSPs, and the telecommunications industry. The contemporary network topologies will be transformed to automatically identify the best routing path through a dedicated and highly sensitive network to meet the business and customer demands which reflect a logical evolution. Is network slicing. 3. Network slicing makes it possible to provide service differentiation and achieve end-user service level agreements, SLAs, with the most economical model. The ultimate potential with network slicing will open new types of service offerings and endorse various business models in a scalable manner with a high pace of service delivery. It is an enabler for the service provider to generate more revenues, but at lower prices than with reasonable options, and robustness of the network maintained or improved. Network slicing is often discussed as a benefit of moving to the 5G standalone SA, and it is reviewed as one of the essential enablers in 5G System 5. One of the primary advantages of network slicing is that network slices can be designed explicitly to accommodate those use cases whether it is smart home, Internet of Things, IoT, the vehicle-to-vehicle, V2V, communication between car or the smart power system. Every use case undergoes a specific collection of tailored resources in a complex network configuration containing some service-level agreement-specified variables such as bandwidth, speed, and availability that all match the application's needs. While it is very appealing that network slicing can change all industries and help in 5G network evolution, whereas, it'll take time for the network operators to move from the existing network, largely manually operated, to a fully automated smart network that incorporates network slicing. 10. Many of the operators are taking small steps towards migrating to 5G SA, while they have started with deploying non-standalone 5G which uses most of 4G core network. As 5G NSA doesn't incorporate automation and network virtualization. Transforming from 5G NSA to 5G SA will help operators to assimilate the more virtual network functions that enable network slicing. 12. Conclusion 5G brings several capacity improving features, like spectral efficiency, new centimeter and millimeter frequency bands, massive MIMO and beamforming, and scalable lower radio latency. Introducing multi-connectivity improves reliability and capacity for end-to-end 5G needs. 5G also includes specific features that enable massive connectivity and high-throughput capabilities. Network slicing and 5G together incorporate capabilities from technologies such as software-defined networking, SDN, NFV, orchestration, and analytics. These network slices will have a more important function, as they can be designed, deployed, and customized although run on a common network framework. The sharing of this framework helps reduce its costs.